Imagine holding in your hands a machine that changed the course of human history, a device no larger than a typewriter, yet capable of generating billions upon billions of possible encrypted messages. This is the Enigma Machine, and today we're going to explore 100 fascinating facts about one of the most remarkable inventions of the 20th century. The Enigma Machine was an electromechanical cipher device used primarily by Nazi Germany during World War II to protect military communications. At first glance, it resembled an ordinary typewriter housed in a wooden box, but beneath its deceptively simple exterior lay an ingenious system of rotating wheels and electrical pathways that could scramble messages into seemingly unbreakable code. When an operator pressed a key, an electrical signal would travel through a complex maze of wiring, causing a different letter to illuminate on a lamp board above the keyboard. What made this device truly extraordinary was that the same letter would almost never encrypt to the same output twice in a row. The word enigma comes from the Greek word enigma, meaning riddle or mystery. This name was perfectly chosen, as the machine would go on to create some of the most perplexing puzzles in the history of cryptography. The device was invented by a German engineer named Arthur Skerbius at the end of World War I. Skerbius founded a company called Skerbius and Ritter in Berlin, and he patented his invention on February 23, 1918. His initial vision wasn't military at all. He saw the Enigma as a commercial product that could protect business communications and trade secrets for banks, companies, and corporations. The first Enigma machines were actually offered to the commercial market in the early 1920s. These early commercial models were bulky, expensive devices that looked quite different from the military versions that would later become famous. One of the earliest models, called Enigma A, was first exhibited at the Congress of the International Postal Union in 1923. It weighed about 50 kilograms and was far too heavy and impractical for most businesses. The commercial market showed little interest, and sales were disappointing. Banks and businesses simply didn't see the need for such sophisticated encryption, and the machines were prohibitively expensive. However, what the commercial sector rejected, the military embraced. The German military, still reeling from defeat in World War I and bound by the restrictions of the Treaty of Versailles, saw enormous potential in Skerbius's invention. In 1926, the German Navy became the first military branch to adopt the Enigma machine, followed shortly by the German Army in 1928. The military versions were modified to be more portable, more rugged, and more secure than their commercial predecessors. This military adoption would transform the Enigma from a failed commercial product into one of the most significant weapons of the Second World War. At its core, the Enigma machine operated on a principle of polyalphabetic substitution. This means that each letter in the plaintext message could be encrypted as a different letter depending on the position of rotating wheels inside the machine. Unlike simple substitution ciphers, where A might always become G, the Enigma constantly changed its encryption pattern with each keystroke. This made traditional frequency analysis, where codebreakers look for common letters like E or T in English, completely useless. The Germans believed this made their communications virtually unbreakable, and for a time, they were right. The heart of the Enigma machine consisted of 3, or sometimes 4 rotating wheels called rotors. Each rotor was a disc about 10 centimeters in diameter, made of hard rubber or bakelite, with 26 electrical contacts on each side, representing the 26 letters of the alphabet. Inside each rotor was a complex pattern of wiring that connected each input contact to a different output contact. When electrical current entered one side of a rotor at a particular letter position, it would exit at a completely different letter on the other side. The genius of the system was that after each key press, at least one rotor would advance by one position, changing the entire encryption pathway for the next letter. The mathematical security of the Enigma was staggering, with 3 rotors chosen from a set of 5, each starting at any of 26 possible positions, and a plug board that could swap 10 pairs of letters. The total number of possible configurations exceeded 150 million, or 158 quintillion 962 quadrillion, 555,217,826,360,000 to be exact. To put this in perspective, if you had started testing one configuration every second at the beginning of the universe, you would still be testing configurations today. The Germans were confident that even if the Allies captured an Enigma machine, they could never break the code through brute force alone. But the Enigma had a crucial weakness, one that would ultimately lead to its downfall. The machine could never encrypt a letter as itself. If you pressed the letter A, the output could be any letter from B to Z, but it could never be A. This seemingly minor design feature was actually a deliberate choice made by the inventors to prevent errors in transmission. If a letter could encrypt as itself, operators might confuse encrypted messages with plaintext. However, this quirk would give codebreakers a vital clue. They knew that wherever they saw a particular letter in an encrypted message, the corresponding position in the original message absolutely could not contain that same letter. By the outbreak of World War II in September 1939, thousands of Enigma machines were in use across all branches of the German military. The Wehrmacht, the Kriegsmarine, the Luftwaffe, the SS, and even German intelligence services all relied on Enigma encryption for their most secret communications. The Germans had such faith in their cipher system that they transmitted everything from strategic military plans to supply logistics to frontline battlefield reports using Enigma. Hitler himself believed the system was unbreakable, and German military leadership operated under the assumption that their communications were completely secure from enemy interception. They would discover, far too late, that this assumption was dangerously wrong. To truly understand how the Enigma machine created its seemingly impenetrable codes, we need to examine the intricate mechanical and electrical systems that made it work. Let's journey inside this remarkable device and discover the engineering brilliance that made it both a masterpiece of cryptography and, ultimately, a puzzle that could be solved. The plug board, or Steckerbrett in German, was located at the front of the military Enigma machines and looked like an old-fashioned telephone switchboard. It consisted of 26 sockets, one for each letter of the alphabet, arranged in 2 rows. Operators would insert cable plugs to swap pairs of letters before and after the main encryption process. For example, if you connected A to M with cable, then every time you pressed A on the keyboard, it would first be changed to M before entering the rotors, and likewise M would become A. On a standard military Enigma, 10 cables were used, swapping 10 pairs of letters and leaving 6 letters unswapped. This plug board added an additional layer of security that multiplied the number of possible settings astronomically. The keyboard itself was laid out like a standard German typewriter of the era, arranged in the QWERTZ configuration rather than the QWERTY layout familiar to English speakers. The keyboard contained 26 keys, one for each letter, but interestingly, there were no keys for numbers or punctuation marks. All numbers had to be spelled out as words, and punctuation was either omitted or indicated by special letter combinations. For instance, the letter X was often used to represent a period or full stop, while the sequence QQ might indicate quotation marks. This limitation was actually a security feature in disguise, as it reduced the complexity of the machine and made it more reliable in harsh battlefield conditions. Above the keyboard sat the lamp board, a panel containing 26 small circular windows, each with a letter of the alphabet. Behind each window was a small light bulb that would illuminate when that letter was the encrypted output. When an operator pressed a key, the corresponding encrypted letter would light up on the lamp board, and the operator's assistant would write down this illuminated letter. The lamps were powered by the same electrical circuit that ran through the machine, and they were deliberately dimmed to prevent light from escaping the machine in dark conditions where operational security was critical. Some models used in submarines and aircraft had even dimmer lamps or special covers to prevent any light leakage. The rotors, also called wheels or drums, were the true heart of the Enigma's encryption system. Each rotor was approximately 10 centimeters in diameter and about 1 centimeter thick. On the right face of each rotor were 26 brass spring-loaded pins arranged in a circle, and on the left face were 26 corresponding flat circular contacts. Inside each rotor was a unique pattern of insulated wiring that connected each pin on one side to a contact on the other side in a scrambled arrangement. No 2 rotors had the same internal wiring pattern. The German military used different rotor designs throughout the war, with the most common system involving a set of 5 rotors, from which 3 would be selected and installed in the machine for any given day's operations. Each rotor had a ring around its circumference, marked with the 26 letters of the alphabet or the numbers 1 through 26. This ring could be adjusted and locked into any of 26 positions relative to the internal wiring of the rotor. This ring setting, called the Ringstellung in German, added yet another layer of complexity to the encryption. The ring setting determined the point at which each rotor would cause the next rotor to its left to advance, similar to how the minute hand on a clock causes the hour hand to advance. Adjusting the ring setting was a delicate operation that required a special tool, and getting it wrong would make decryption impossible even with the correct keys. The rotors didn't all move at the same rate, which was crucial to the Enigma security. The rightmost rotor, called the fast rotor, would advance one position with each key press, just like the second hand on a clock. The middle rotor would advance one position each time the fast rotor completed a full rotation of 26 steps. The leftmost rotor would advance when the middle rotor reached a specific position and moved forward. However, there was a peculiar mechanical feature called the double-stepping anomaly. Due to the way the mechanical pawls and ratchets were designed, the middle rotor would sometimes advance two positions in quick succession, causing both the middle and left rotors to step together. This quirk was not a design flaw, but rather an unavoidable consequence of the mechanical implementation, and it became another characteristic that codebreakers had to understand. At the left end of the rotor assembly sat one of the most ingenious components of the Enigma system, the reflector, or Umkewals. The reflector was essentially half a rotor with 13 wires inside that connected pairs of contacts together. When the electrical signal passed through all three rotors from right to left, it would enter the reflector, which would send it back through the rotors again, from left to right along a different path. This meant that the encryption process was symmetrical. Encrypting a message and decrypting it used exactly the same machine settings. If you set up two Enigma machines identically and typed an encrypted message into one, the plaintext would appear on the other. This symmetry was operationally convenient but cryptographically significant, and it would provide important clues to codebreakers. The reflector also had a profound consequence. It made the Enigma's fatal flaw inevitable. Because the reflector sent the signal back through the rotors, and because the wiring ensured that no contact could connect to itself, no letter could ever encrypt as itself. The reflector made it mechanically impossible for A to become A, or for B to become B. While this seemed like a minor inconvenience, it was actually a devastating weakness. It meant that codebreakers could immediately eliminate certain possibilities when analyzing encrypted messages, dramatically reducing the search space they needed to explore. The electrical pathway through an Enigma machine was a marvel of 1920s engineering. When an operator pressed a key, a mechanical arm would close an electrical contact, sending current from the battery through the plug board, then through the rightmost rotor, the middle rotor, the leftmost rotor, into the reflector, and then back through all three rotors in reverse order, through the plug board again, and finally to one of the lamps on the lamp board. This entire journey happened in a fraction of a second. The current would take a different path through the maze of wires, depending on the position of each rotor, which is why the same keystroke would produce different encrypted letters as the rotors advanced. The power source for the Enigma was remarkably simple, a standard battery, usually about 4.5 volts. Some models used dry cell batteries that could be easily replaced in the field, while others used rechargeable accumulators. The low voltage requirement meant the machine was relatively safe to operate and maintain. The electrical current flowing through the machine was quite weak, just enough to illuminate the small bulbs behind the lamp board. This low power consumption was essential for portable military use, as it meant a single set of batteries could last for thousands of encryptions before needing replacement. The encipherment strength of the Enigma increased exponentially with each additional element. The three rotors alone, if they were selected from a set of 5 and could start at any position, provided 60 possible rotor orders multiplied by 17,576 possible starting positions, giving over 1 million combinations. Add the ring settings, and this multiplied by another 17,576 possibilities. Then the plug board contributed approximately 150,738,274,937,250 different ways to connect 10 pairs of letters. Multiply all these factors together, and you arrive at that astronomical figure. More than 158 million possible configurations. However, not all these settings were used in practice. The German military distributed codebooks that specified which rotors to use, their order, their starting positions, their ring settings, and which letters to connect on the plug board. These settings would typically change daily at midnight, and sometimes more frequently for highly sensitive communications. Every Enigma operator in a particular network needed identical settings to communicate. If even one setting was wrong, decryption would fail, producing gibberish. This created a massive key distribution problem that the Germans had to solve through careful operational procedures and secure courier networks. The mechanical precision required to manufacture an Enigma machine was impressive for its era. Each rotor had to be machined to exact tolerances to ensure proper electrical contact between the pins and the contacts. The wiring inside had to be carefully soldered to create the scrambling pattern without any shorts or breaks. The springs behind each pin had to provide consistent pressure to maintain good electrical contact, even as the rotors wore down from repeated use. The entire assembly had to be robust enough to function in the harsh conditions of submarines, aircraft, and battlefield command posts. German engineering excellence was evident in every component. The Enigma also had a mechanical security feature that prevented casual inspection of the internal wiring. The rotors were housed in a covered compartment that could only be opened with special care. The wiring itself was embedded in hard rubber or bakelite, making it extremely difficult to trace without destroying the rotor. Even if an enemy captured an intact Enigma machine, understanding the exact wiring pattern of each rotor would require careful testing or X-ray examination. The Germans believed that even with a captured machine, enemies would need months of painstaking work to reverse engineer the rotor wirings, by which time the daily settings would have changed thousands of times. One often overlooked component was the importance of the machine's carrying case. Military Enigma machines were housed in wooden boxes designed to protect the delicate mechanism during transport. These boxes were typically made of oak or similar hardwoods, with leather handles and metal corner reinforcements. Inside, the machine was secured with leather straps or spring clips. The lid of the case often held spare parts, including extra bulbs for the lamp board, spare cables for the plug board, and sometimes even the code books specifying daily settings. Some cases had special compartments for pencils, message pads, and the wooden blocks used to support the machine at a comfortable typing angle. The Enigma machine was not a single device, but rather a family of related machines that evolved over more than 2 decades. From the early commercial prototypes to the highly sophisticated military variants, each version represented an attempt to balance security, portability, and ease of use. Understanding these different models reveals how cryptographic technology advanced during one of history's most critical periods. The very first Enigma model, known as Enigma A, or the glow lamp machine, was demonstrated in 1923. This behemoth weighed approximately 50 kilograms and stood nearly half a meter tall. It used a typewriter mechanism that would automatically print the encrypted letters onto paper, eliminating the need for a separate operator to read and transcribe the lamp board. However, this printing mechanism made the device heavy, expensive, and prone to mechanical failure. Only a handful were ever manufactured, and it quickly became apparent that this design was impractical for commercial use. The Enigma B model followed shortly after and was slightly more refined, though still intended for the commercial market. It retained the heavy typewriter printing mechanism, but improved the overall reliability. Like the Enigma A, it saw minimal commercial success. These early failures taught Arthur Skerbius and his engineers valuable lessons about what the market actually needed: something lighter, more reliable, and significantly cheaper. The printing mechanism, while elegant in theory, was the primary source of problems, and it would be abandoned in subsequent models. The Enigma C model marked a significant turning point in the device's evolution. Introduced around 1924, it eliminated the printing mechanism entirely and instead used the lamp board system that would become the standard for all future military models. This change reduced the weight to about 12 kilograms and dramatically improved reliability. The Enigma C was housed in a flat box and looked much more like the iconic Enigma machines we recognize today. It featured 4 rotors instead of 3, which actually made it more secure than the later military versions, though the 4th rotor would eventually be reintroduced in naval models years later. The Enigma D model, also known as the commercial Enigma or Enigma K, was specifically designed for the export market and commercial customers. It was produced throughout the 1920s and into the early 1930s. This model used 3 rotors selected from a set of 3, making it simpler and cheaper to manufacture than the Enigma C. Crucially, the commercial Enigma lacked the plug board found on military models, which significantly reduced its security. The rotor wirings were also different from military versions. Several dozen of these machines were sold to businesses, foreign governments, and even other military organizations, including the Italian and Spanish navies. The fact that these commercial machines were available on the open market would later prove significant for Allied code-breaking efforts. The Wehrmacht Enigma, also designated as Enigma I, became the standard German Army and Air Force machine from 1930 onward. This was the model most widely used throughout World War II. It featured 3 rotors, selected from a set of 5, a plug board with room for up to 13 cable connections, though usually only 10 were used, and a reflector. The machine weighed about 12 kilograms in its wooden carrying case, and was portable enough for field use. The Enigma I went through several minor revisions during the war, with improvements to durability and ease of use, but the fundamental design remained remarkably consistent. The Enigma M3, used by the German Navy or Kriegsmarine, was essentially identical to the Wehrmacht Enigma I in physical appearance and operation, but it used a completely different set of rotors with different internal wirings. The Navy used 8 rotors, labeled with Roman numerals from I to 8, from which 3 would be selected for daily operations. This meant that naval Enigma messages could not be decrypted using captured Army Enigma rotors, and vice versa. The Navy also used different reflectors and maintained separate key distribution networks. This compartmentalization was a sound security practice that forced the Allies to essentially break 2 different Enigma systems. In February 1942, the German Navy introduced the Enigma M4, a devastating upgrade that created what the Allies called the blackout. The M4 featured 4 rotors instead of 3, specifically for communications with U-boats in the Atlantic. The 4th rotor didn't rotate during normal operation, but instead acted as a selectable reflector, coming in 2 versions called Beta and Gamma. This modification increased the number of possible settings by a factor of 26 and restored security to German naval communications, just when the Allies had been making progress against the M3. The blackout lasted for 10 months, during which Allied intelligence could not read U-boat messages, contributing to devastating shipping losses in the Atlantic. The physical accommodation of a 4th rotor in the M4 required clever engineering. Rather than making the entire machine larger, German engineers made the reflector thinner, creating just enough space for the additional rotor within the existing case dimensions. This meant that M4 machines looked externally identical to M3 machines, making them difficult to distinguish from a distance. The 4th rotor, however, made the M4 incompatible with the 3-rotor M3. If someone tried to send an M4 encrypted message to an M3 machine, even with all other settings correct, the decryption would fail. This incompatibility required U-boats to carry both M3 and M4 machines during the transition period. Several specialized Enigma variants were created for specific purposes. The Enigma G, also known as the Zollwerk Enigma or counter machine, was developed for the German Army High Command and the Abwehr, the military intelligence service. It used a completely different stepping mechanism with rotors that advanced in irregular patterns rather than the regular odometer-style stepping of standard Enigmas. The Abwehr Enigma also featured 4 rotors and a different reflector design. It was more secure in some ways, but also more complex to operate. Only about 100 Abwehr Enigmas were ever manufactured, making them extremely rare today. The Enigma T, nicknamed Tirpitz after the German battleship, was designed specifically for secure communications between Berlin and Tokyo. It featured a typewriter-style printer mechanism, returning to the concept abandoned in the earliest models, but with much improved reliability. The Enigma T was never widely deployed, and very few examples survived the war. Its existence demonstrates that German cryptographers continued experimenting with different designs even during the height of the conflict. The Luftwaffe, or German Air Force, primarily used the standard Enigma machine, but with their own specific rotor selection and settings. They did experiment with a modified version featuring a modified reflector called Unkerwalls D, or UKWD, which was rewirable. This means that rather than having fixed internal wiring like earlier reflectors, operators could manually change the connections using a plug system. The rewirable reflector dramatically increased the number of possible configurations, but also increased the complexity of daily setup procedures. It was introduced in 1944, but saw limited deployment before the war ended. The Swiss K model deserves special mention as a fascinating variant. After World War II, Switzerland purchased commercial Enigma machines and modified them for their own military use. They replaced the rotors with newly designed ones featuring different wiring patterns and added a mechanical printing mechanism. The Swiss continued using modified Enigma machines into the 1970s, long after the original German models had been retired. They believed their modifications made the machines secure, unaware that British and American intelligence agencies had likely retained the ability to break Enigma-based encryption systems. Different variants also emerged based on operational requirements. Portable field versions were built with carrying straps and weatherproofed cases for frontline infantry use. Naval versions featured specially sealed components to protect against moisture and salt spray in submarine and ship environments. Some aircraft versions were built with dimmer lamps and vibration-dampening mounts. In occupied territories, local workshops sometimes produced simplified copies or repair parts, leading to additional unofficial variants with slight modifications from standard specifications. The evolution of rotor designs themselves tells an important story. The original commercial Enigma rotors had their wiring patterns chosen somewhat arbitrarily. The military rotors, however, were carefully designed to maximize cryptographic strength. The turnover notch, which determined when each rotor would cause the next one to step, was positioned differently on each rotor. Rotors I through V had their notches at different positions, meaning that selecting different rotors didn't just change the wiring, but also changed the stepping pattern. The later rotors 6, 7, and 8, introduced for naval use, actually had 2 turnover notches each, causing the next rotor to step twice per rotation. An interesting variant that never reached production was a proposed 5-rotor Enigma for extremely high-security communications. German engineers designed this version in the later stages of the war, recognizing that Allied cryptanalytic capabilities were improving. However, the added complexity, manufacturing cost, and operator training requirements made it impractical. By the time this design was ready for production, German industrial capacity was severely strained, and resources couldn't be spared for upgrading encryption equipment when tanks, aircraft, and ammunition were desperately needed. The reflector designs also evolved throughout the Enigma's development. The earliest reflectors, designated Unkerwalls A or UKWA, were used in commercial and early military machines. These were replaced by UKWB, which became the standard reflector for most Wehrmacht machines throughout the war. Later, UKWC was introduced with different internal wiring to provide additional security. Each reflector change required new codebooks to be distributed and forced codebreakers to restart portions of their analytical work. The Germans correctly understood that changing reflectors enhanced security, but they underestimated how quickly Allied codebreakers could adapt. Some Enigma machines were modified in the field by units that felt standard security procedures were insufficient. Certain Luftwaffe units allegedly experimented with using more than 10 plugboard cables, filling all 13 available sockets. Some submarine commanders were rumored to have modified their encryption procedures by adding extra encipherment steps or using non-standard indicator systems. These unauthorized modifications sometimes made individual messages more secure, But they also created compatibility problems and sometimes made messages easier to break because they deviated from established patterns that codebreakers had learned to exploit. The production of Enigma machines was a significant industrial undertaking. The primary manufacturer was Heimsoeth und Rinke in Berlin, though other companies also produced components or complete machines under license. At peak production during the war, dozens of Enigma machines were being manufactured each day. The machines required skilled craftsmen to assemble and test, with each rotor needing to be individually wired and calibrated. Quality control was essential, as even minor defects in contact springs or wiring could cause encryption failures. Despite the industrial pressures of wartime production, German manufacturers maintained remarkably high-quality standards for Enigma machines throughout the conflict. One variant that bridged commercial and military use was the railway Enigma, used by the German state railway system, the Reichsbahn. These machines were used to encrypt communications about train schedules, logistics, and cargo shipments, much of which supported military operations. The railway Enigma used yet another set of rotors with unique wirings, and it employed 3 rotors, selected from a set of 3, like the early commercial machines. Because railway communications were less time-sensitive than battlefield messages, railway Enigma security procedures were sometimes more relaxed, which would create vulnerabilities that Allied codebreakers learned to exploit. The true story of the Enigma machine is not just about the technology itself, but about how it was used in the daily operations of the German military during World War II. Every day, across thousands of locations from the Arctic Circle to the deserts of North Africa, German radio operators sat down at their Enigma machines to send and receive the encrypted messages that coordinated the largest military force ever assembled. Understanding these operational procedures reveals both the discipline of the German military and the human errors that would ultimately compromise their communications. Each day at midnight, new Enigma settings would come into effect across the German military networks. These daily keys were distributed in codebooks printed on water-soluble paper that could be quickly destroyed if capture seemed imminent. A typical monthly codebook would contain 30 or 31 pages, one for each day, specifying the rotor selection, rotor order, ring settings, plug board connections, and initial rotor positions. These codebooks were among the most closely guarded documents in the German military. Officers responsible for them carried them in special pouches, often chained to their bodies, and were under orders to destroy them immediately if their position was overrun. The daily key setup procedure was a carefully choreographed ritual that every Enigma operator had to master. First, the operator would consult the codebook for the current date and note all the settings. They would then select the correct 3 rotors from the wooden box containing the full set, carefully checking the Roman numeral marking on each rotor's rim. The rotors would be installed in the specified order, from left to right. Next came the delicate task of setting the ring positions. Each rotor had to be removed, its ring loosened with a special pin tool, rotated to the specified letter or number, and then locked back in place. After reinstalling the rotors with their adjusted rings, the operator would set the starting positions by rotating each rotor until the correct letters appeared in the small windows visible on the top of the machine. Finally, they would insert the 10 plugboard cables to connect the specified letter pairs. The actual process of sending a message involved several steps beyond simple encryption. First, the sender would compose the message in German, removing all punctuation and spaces, creating one continuous string of letters. Numbers would be spelled out as words, so 5 became Fuenf, and 1942 became YNSNUNVRNULLZWEI. The operator would then choose a 3-letter message key, which was the actual starting position the rotors would be in when encrypting this specific message. This message key was itself encrypted using the daily key settings and transmitted at the beginning of the message. The operator would then manually rotate the rotors to the chosen message key position and begin encrypting the actual message content, pressing each letter on the keyboard and having an assistant write down the illuminated letters that appeared on the LAN board. Radio transmission procedures added another layer of complexity to the system. The encrypted message would be sent via Morse code by a radio operator who typically didn't have access to the Enigma machine itself. The message would be prefaced with a call sign identifying the receiving station, a timestamp, and the encrypted message key. The receiving station's radio operator would transcribe the Morse code message, which would then be handed to their Enigma operator. That operator would use the daily key settings to decrypt the encrypted message key, set their rotors to that position, and then decrypt the main message body. Any error in transcription, any mistake in settings, or any mechanical malfunction would result in gibberish output, requiring the message to be retransmitted. The German Navy operated under particularly strict communication security procedures due to the critical importance of submarine operations. U-boat commanders were instructed to maintain radio silence whenever possible, transmitting only essential reports about convoy sightings, attacks, or their own status. When they did transmit, messages were supposed to be brief, preferably under 50 letters. The Navy developed an elaborate system of short signal codebooks that allowed commanders to convey common information using abbreviated codes that would then be encrypted by Enigma. For example, a short weather report or position update might be reduced to just a few letter groups before encryption. One of the most important categories of German messages was the weather report. Weather stations across occupied Europe and aboard ships at sea would transmit regular meteorological observations encrypted with Enigma. These reports followed a rigid format that always began with the same German word Wetter, meaning weather. This predictable beginning of so many messages would become a critical weakness that Allied codebreakers learned to exploit. If you knew a message started with Wetter, you suddenly had a crib, a piece of known plaintext that could be used to work backwards and discover the day's settings. Another category of highly predictable messages came from situation reports or Leitmeldungen. Every morning at 6 o'clock, German units across all fronts were required to send a situation report to higher headquarters. These reports often followed formulaic patterns, beginning with phrases like kein besonderen Ereignis, meaning nothing special to report. The sheer number of these routine reports, combined with their predictable timing and often repetitive content, provided Allied codebreakers with an abundance of cribs to work with. The German military's emphasis on regular reporting, while operationally sensible, created cryptographic vulnerabilities. Security procedures evolved throughout the war as the Germans became aware, or at least suspicious, that their codes might be compromised. Early in the war, the message key procedure had a significant weakness. Operators would choose a 3-letter key, encrypt it twice using the daily settings, and transmit both encrypted versions at the start of the message. This double encryption was intended to catch transmission errors, but it created a pattern that cryptanalysts could exploit. In May 1940, the Germans changed this procedure, with operators encrypting the message key only once and using different methods to guard against errors. This change significantly disrupted Allied code breaking for a time. The physical security of Enigma machines was taken extremely seriously. Machines were numbered and tracked, with detailed logs maintained of their location and responsible officer. If a unit retreated, standing orders required Enigma machines to be evacuated with higher priority than most other equipment except weapons. If evacuation was impossible, the machines were to be thoroughly destroyed. Rotors were to be removed and smashed, preferably with the pieces scattered. The wooden cases were to be burned. Codebooks were always to be destroyed before the machine itself. Despite these precautions, Allied forces did manage to capture intact or partially intact Enigma machines on several occasions. One famous incident occurred in May 1941 when the British destroyer HMS Bulldog captured the German submarine U-110. The submarine had been forced to surface after depth charge damage, and British boarding parties reached it before the Germans could complete their scuttling procedures. They recovered an intact Enigma M3 machine, current codebooks, and other cryptographic materials. The captured materials were immediately rushed to Bletchley Park and proved invaluable. The Germans never realized U-110 had been captured because it eventually sank, and they assumed all hands and materials had been lost. This capture significantly accelerated British efforts to break naval Enigma. Field security practices varied considerably across different units and branches of service. Elite units like the SS and the Abwehr Intelligence Service generally maintained stricter procedures. Frontline combat units, especially those under heavy pressure, sometimes became lax about security protocols. There are documented cases of operators choosing weak message keys, like AAA, or obvious patterns like ABC, which made cryptanalysis easier. Some operators, through fatigue or carelessness, would reuse the same message key for multiple messages, another serious breach that created patterns for codebreakers to exploit. The Germans did implement various security measures beyond the machine itself. Operators were trained never to use the same message key twice, though this rule was frequently violated. They were instructed to compose messages that avoided repetitive phrasing and predictable content. Though military communication by its nature tends toward standardization, random letter groups were sometimes inserted into messages to increase their apparent randomness, though this made messages longer and potentially increased the chance of transmission errors. Some units experimented with sending dummy traffic, encrypted meaningless messages intended to confuse traffic analysis by Allied intelligence. One particularly sensitive category of messages involved the Enigma key settings themselves. When new codebooks were distributed or when settings needed to be changed outside the normal daily schedule, these changes had to be communicated securely. Sometimes higher headquarters would send these keys for keys over separate secure channels, using different encryption systems or even one-time pads. Other times, they would be delivered by motorcycle courier or aircraft. The logistics of key distribution across a continental empire became increasingly difficult as the war turned against Germany, and Allied air superiority made travel dangerous. Different theaters of war presented unique operational challenges. In North Africa, Enigma machines had to operate in extreme heat and dust. Sand infiltration could cause electrical contacts to fail or rotors to bind. Special maintenance procedures were developed, including more frequent cleaning and the application of dry lubricants rather than oils that would attract sand. In the Arctic, extreme cold could make the rubber and bakelite rotors brittle and could drain batteries rapidly. Operators in Norway and Finland had to keep their machines and spare batteries warm, sometimes carrying them inside their uniforms. The Eastern Front presented perhaps the harshest operational environment. The vast distances, poor infrastructure, and extreme weather conditions all created challenges for maintaining secure communications. As German forces advanced deep into the Soviet Union in 1941 and 42, supply lines for codebooks and spare parts stretched thousands of kilometers. When the tide turned and German forces were pushed back, the chaos of retreat led to numerous security breaches. Enigma machines were abandoned, codebooks were not properly destroyed, and communication procedures broke down. Soviet intelligence captured numerous Enigma machines, though they appear to have had limited success in breaking the codes, possibly due to lack of sufficient intercepted traffic or cryptanalytic expertise. At sea, U-boat operations required special considerations. The cramped confines of a submarine meant the Enigma machine had to be secured against the violent motion during depth charge attacks or emergency dives. The machine was typically mounted in the radio room, which was one of the most cramped spaces aboard. The combination of a skilled radioman and Enigma operator had to work in coordination, often under combat stress. The need for radio silence meant that messages would often be composed and encrypted in advance, then transmitted in rapid bursts to minimize the chance of direction finding by Allied forces. Strategic bomber operations by the Luftwaffe also generated significant Enigma traffic. Flight plans, target assignments, weather conditions, and mission outcomes all had to be communicated. The predictable timing of these communications, often occurring in the hours before major raids, allowed Allied intelligence to anticipate attacks. In some cases, decrypted Enigma messages provided enough advance warning for British air defenses to be positioned optimally or for valuable aircraft to be dispersed from threatened airfields. The Germans never fully appreciated how much their operational planning was being revealed by this decrypted traffic. The logistics network supporting German military operations generated enormous volumes of Enigma traffic. Supply requests, transport schedules, fuel allocations, ammunition deliveries, and personnel movements all required encrypted communications. This administrative traffic, while perhaps less dramatic than frontline battle reports, provided Allied intelligence with comprehensive understanding of German military capabilities. Logistics messages often contain specific numbers, unit designations, and location names that could be cross-referenced with other intelligence sources. A message about fuel deliveries to a particular unit might reveal the location of that unit's headquarters. Reports of supply shortages indicated which sectors were under strain. As Allied bombing campaigns intensified, the Germans faced increasing challenges maintaining their Enigma communication networks. Manufacturing facilities were bombed, disrupting production of new machines and spare parts. Transportation networks were attacked, making distribution of codebooks irregular. Communication infrastructure like radio towers and telephone lines were destroyed, forcing greater reliance on wireless transmission that could be intercepted. The degradation of Germany's communication security was not primarily due to the Enigma being broken, but rather due to the entire system surrounding it being progressively dismantled by the Allied war effort. In the final months of the war, Enigma usage became increasingly desperate and disorganized. Units cut off from higher command continued using outdated codebooks. Some operators, knowing the war was lost, became careless about procedures. Others maintained perfect discipline to the very end, destroying their machines and codebooks even as Allied forces closed in. When Germany surrendered in May 1945, thousands of Enigma machines were captured intact across Europe. The Western Allies quietly took possession of as many as possible, while Soviet forces captured thousands more in Eastern Europe and Germany itself. The fate of these captured machines would have implications for cryptography and intelligence work for decades to come. Long before Bletchley Park became synonymous with code breaking, and years before Alan Turing made his legendary contributions, a small group of brilliant Polish mathematicians achieved what the Germans believed was impossible. They broke the Enigma code. This story of Polish ingenuity, mathematical brilliance, and desperate courage is one of the most remarkable yet underappreciated chapters in the history of cryptography. Without the Polish foundation, the later Allied success against Enigma would have been impossible. Poland's geographic position made it acutely aware of the German threat. Sandwiched between Germany and the Soviet Union, Poland understood that another European war would likely mean invasion from one or both neighbors. In the 1920s, Polish military intelligence, known as the Bureau Cyfro or Cipher Bureau, began intercepting German military radio transmissions. When these transmissions suddenly became incomprehensible in the late 1920s, the Poles correctly deduced that Germany had adopted machine encryption. They managed to obtain a commercial Enigma machine, but quickly discovered that the military version must use different rotor wirings and additional security features. The Polish approach to code breaking was revolutionary because it relied on mathematics rather than linguistics. Traditional cryptanalysis had been dominated by linguists who understood patterns in language, frequency of letters, and common word structures. The Poles recognized that Enigma's mechanical nature meant it could potentially be defeated through mathematical analysis. In 1929, the Cipher Bureau recruited mathematicians from Poznan University, specifically seeking young men who also understood German. This combination of mathematical skill and language knowledge would prove crucial. 3 young mathematicians would form the core of the Polish Enigma-breaking effort. Marian Rejewski, Jerzy Rzycki, and Henryk Zygalski were all in their early 20s when they joined the Cipher Bureau. They brought fresh perspectives unburdened by traditional cryptanalytic assumptions. Rejewski, in particular, would make the crucial breakthrough that demonstrated Enigma could be broken mathematically. His work began in December 1932, when he was given the task of analyzing German Enigma traffic full-time. Rejewski's first major insight involved understanding the permutation structure created by the Enigma's components. He recognized that each element of the machine, the plugboard, rotors, and reflector, created a mathematical permutation of the alphabet. By treating these as elements of group theory, he could express the entire encryption process as a series of mathematical transformations. This abstraction was brilliant because it allowed him to analyze the machine's behavior without initially knowing the exact wiring of the rotors. He was essentially working backwards from the effects to deduce the causes. The critical breakthrough came from a weakness in the early German message procedure. Operators would choose a three-letter message key, then encrypt it twice using the daily settings before transmitting it. This meant the first and fourth letters of each encrypted message header were actually the same plaintext letter, encrypted at the same rotor positions, just seconds apart before any rotors had stepped. The same was true for the second and fifth letters, and the third and sixth letters. Rejewski realized this relationship created chains of letters that remained consistent regardless of the plugboard settings. By cataloging these chains across many messages from a single day, he could work out the internal wirings of the rotors. However, Rejewski still needed one crucial piece of information: the wiring between the keyboard and the entry point of the first rotor. The Germans had not used simple alphabetical order, but had scrambled this connection. Without knowing this wiring pattern, Rejewski could make no further progress. Then, in a stroke of luck in late 1932, French intelligence provided the Polish Cipher Bureau with documents obtained from a German spy named Hans Thilo Schmidt. These documents included some daily key settings. With this information, Rejewski was able to work backwards and determine the keyboard-to-rotor wiring. By the end of 1932, he had successfully reconstructed the internal wirings of all three rotors used in the German military Enigma. This achievement was extraordinary. Rejewski had reverse-engineered the secret internal structure of the Enigma rotors through pure mathematical deduction, using only intercepted messages and understanding of the machine's general principles. The Germans had believed that even if an enemy obtained an Enigma machine, discovering the rotor wirings would take months of painstaking work. Rejewski did it in weeks, without a complete machine, using nothing but pencil, paper, and mathematical insight. By January 1933, the Polish Cipher Bureau was reading German Enigma messages regularly. The Poles didn't simply read messages manually. They created mechanical devices to automate and speed up the code-breaking process. Rejewski designed a machine called the Bombe cryptologiczna, or cryptologic bomb, which had nothing to do with explosives. The name possibly came from the ticking sound it made, or from a popular Polish ice cream dessert. The Bombe was an electromechanical device that used 6 Enigma machines wired together in a specific configuration. It would cycle through possible rotor positions, looking for the characteristic chains that Rejewski had identified. When it found a match, it would stop, indicating a possible solution that could be verified manually. By November 1938, the Polish Cipher Bureau had built 6 bombas, each designed to test one possible rotor order. With 3 rotors selected from a set of 3, there were 6 possible arrangements. Each bomba could test its assigned rotor order across all possible initial positions in about 2 hours. This meant that given a few good message intercepts from a particular day, the Poles could usually determine that day's settings within a few hours and read the remaining traffic. The system worked remarkably well until German security improvements in December 1938 dramatically increased the problem's complexity. Henryk Zygalski made another important contribution by developing a manual method that complemented the bombas. He created a system of perforated sheets, now known as Zygalski sheets or the card catalog method. Each sheet corresponded to a different left and middle rotor position, and had holes punched in it at positions that satisfied certain conditions derived from analyzing the message key repetition. By stacking multiple sheets corresponding to different messages and looking for positions where holes aligned on all sheets, cryptanalysts could dramatically narrow down the possible daily settings. This method was more labor-intensive than using the bombas, but could handle situations where machine time was limited. The Polish success continued through the mid-1930s, but the walls were closing in. In December 1938, the Germans increased the number of rotors from 3 to 5, meaning operators now selected 3 rotors from a set of 5 instead of 3 from 3. This increased the possible rotor orders from 6 to 60, a tenfold increase. The Polish Cipher Bureau would have needed 60 bombas instead of 6, an impossible expense for Poland's limited resources. Additionally, in September 1938, the Germans changed the message key procedure again, making the double encryption of the message key more complex. The Poles could still break Enigma, but the process had become far more difficult and time-consuming. By early 1939, war was clearly approaching. Poland faced the likelihood of German invasion and possible Soviet attack from the east. Polish intelligence made a momentous decision. They would share everything they had learned about Enigma with their Western allies. On July 24th and 25th, 1939, in a secret meeting at the Cipher Bureau's facility in the Kabety Woods outside Warsaw, the Poles revealed their Enigma secrets to British and French intelligence representatives. They demonstrated their Bombe machines, explained Rejewski's mathematical methods, provided the reconstructed rotor wirings, and even gave the astonished British and French representatives actual replica Enigma machines that Polish intelligence had constructed. The British representatives at this meeting, including Commander Alastair Denniston from the Government Code and Cipher School and Dilly Knox, a veteran cryptanalyst, were stunned. The British had been working on Enigma for years, with limited success. They had commercial Enigma machines and had made some theoretical progress, but they had not broken the military version. Suddenly, the Poles handed them the complete solution on a silver plate. Knox reportedly could barely believe what he was seeing. The French representative, Captain Gustave Bertrand, who had been the liaison providing the intelligence from Hans Thilo Schmidt, was equally amazed at what the Poles had accomplished with the information he had passed along. Just weeks after this historic meeting, on September 1st, 1939, Germany invaded Poland. The Cipher Bureau staff worked frantically to destroy sensitive documents and evacuate equipment. The Bombe machines were destroyed to prevent capture. Rejewski, Rzycki, Zygalski, and other key personnel fled Warsaw as the German army approached. They made their way to Romania, which was still neutral, and from there eventually reached France. The Polish government in exile established itself in France, and the Polish cryptanalysts continued their work in cooperation with French intelligence services, operating from a facility called PC Bruno near Paris. The Polish contribution cannot be overstated. They had achieved the initial breakthrough that showed Enigma was breakable. They had developed both the theoretical framework and practical methods for exploiting the machine's weaknesses. They had created mechanical devices to automate the process. And crucially, they had shared all of this knowledge with the Allies just in time. When Bletchley Park began its intensive work on Enigma in late 1939 and throughout 1940, they built directly upon the Polish foundation. Every technique used at Bletchley Park, from Turing's bomb to the exploitation of cribs, descended from methods pioneered by Rejewski and his colleagues. After France fell to Germany in June 1940, the Polish cryptanalysts had to flee again. They escaped to unoccupied Vichy France and continued working in secret until November 1942, when Germany occupied all of France. Rejewski and Zygalski managed to escape through Spain to Portugal and eventually reached Britain in 1943. Rzycki had tragically died in January 1942 when the ship he was traveling on struck a mine in the Mediterranean. In Britain, Rejewski and Zygalski worked at a Polish signals facility, but for security reasons, they were not sent to Bletchley Park or told about the ongoing Enigma work there. The British feared that if captured, Polish personnel might be tortured by the Germans, who would be particularly interested in what the Poles knew about Enigma. The Polish mathematician's achievement was rooted in a particular philosophy of approaching code breaking as a mathematical problem rather than a linguistic puzzle. They applied group theory, permutation analysis, and mechanization to create an industrial approach to cryptanalysis. This was a fundamentally different mindset from traditional code breaking, which relied on linguistic intuition, pattern recognition, and painstaking manual work. The Poles essentially invented modern mathematical cryptanalysis, and their methods influenced not just the defeat of Enigma, but the entire subsequent development of cryptology as a mathematical science. The story of the Polish codebreakers remained classified for decades after World War II. When the war ended, the British classified all information about Enigma at the highest level of secrecy. The Polish contribution was not acknowledged publicly. Rejewski returned to Poland after the war and worked as an accountant, unable to speak about his wartime achievements under the communist government. Only in the 1970s, when information about Enigma finally began to be declassified, did the world learn about the Polish breakthrough. Rejewski lived to see his contributions finally recognized, receiving honors from Western governments before his death in 1980. Today, The Polish achievement is properly recognized as the foundation of the entire Allied effort against Enigma. Without Marian Rejewski's initial breakthrough, without the Bombe machines, without the Zygalski sheets, and without the crucial July 1939 meeting, where the Poles shared everything with the Allies, the course of World War II might have been very different. The work at Bletchley Park, as brilliant as it was, built upon a foundation laid by three young Polish mathematicians who saw what others thought impossible and achieved it through pure intellectual determination. Bletchley Park, a Victorian mansion in Buckinghamshire, England, became the nerve center of the Allied war against Enigma. What began as a small operation with a handful of codebreakers grew into an industrial-scale intelligence organization employing over 10,000 people at its peak. The work conducted there, building upon the Polish foundation, would produce intelligence so valuable that some historians estimate it shortened the war by 2 years and saved countless lives. This is the story of how Bletchley Park turned code breaking into a science and intelligence into a war-winning weapon. The Government Code and Cipher School, known as GC and CS, had been working on German code since World War I, but the organization was small and underfunded. In 1938, as war loomed, the decision was made to find a location outside London where code-breaking operations could continue even if the capital was bombed. Bletchley Park was chosen because of its location roughly midway between Oxford and Cambridge universities, providing access to academic talent, and because it sat at a railway junction with excellent communications links. The mansion itself was unremarkable, a sprawling Victorian building with various architectural additions, but its isolated location and existing infrastructure made it perfect for secret work. The initial staff at Bletchley Park in September 1939 consisted of fewer than 200 people, many of them academics recruited from universities. The organization sought mathematicians, linguists, chess champions, crossword puzzle experts, and anyone with demonstrated analytical ability. Perhaps the most famous recruit was Alan Turing, a young mathematician from Cambridge who had already made significant theoretical contributions to computing and logic. Turing arrived at Bletchley Park on the first day of the war and immediately began working on the Enigma problem using the knowledge the Poles had shared. The physical layout of Bletchley Park evolved into a complex of numbered wooden huts, each dedicated to specific tasks. Hut 6 handled German Army and Air Force Enigma traffic. Hut 8, where Turing worked, focused on German naval Enigma. Hut 3 processed and analyzed the decrypted Army and Air Force intelligence, translating it, assessing its importance, and disseminating it to military commands. Hut 4 performed similar functions for naval intelligence. Hut 7 housed intercepted Japanese diplomatic and military traffic. The huts were cramped, poorly heated in winter, and stifling in summer, but they housed some of the most important intellectual work of the 20th century. Alan Turing's first major contribution was redesigning the Polish Bombe concept to handle the increased complexity caused by the German introduction of 5 rotors instead of 3. Turing's Bombe machine was fundamentally different from the Polish version. Rather than looking for the characteristic chains in the message key repetition, which the Germans had made obsolete by changing their procedures, Turing's machine exploited cribs, pieces of known or guessed plaintext. If codebreakers could guess that a particular encrypted message contained a certain word or phrase, they could use that knowledge to test possible Enigma settings. The bomb would mechanically test thousands of possible rotor positions and plug board settings, looking for configurations that would produce the known plaintext from the ciphertext. The first Turing bomb, called Victory, was installed at Bletchley Park in March 1940. It stood about 2 meters tall and contained 30 rotating drums, simulating 30 Enigma rotors in various configurations. Unlike actual Enigma rotors, the bomb drums were wired differently, implementing the logical test Turing had designed. When the machine found a possible match, it would stop, and cryptanalysts would manually verify whether it was the correct daily key. Early versions were unreliable and slow, but British engineer Harold Keane worked with Turing to improve the design. By August 1940, an improved version called Agnus Dei was operational and proved much more effective. Gordon Welchman, another mathematician working in Hut 6, made a crucial enhancement to Turing's bomb design by adding what became known as the diagonal board. This modification exploited additional logical relationships created by the Enigma's plug board, dramatically increasing the machine's efficiency and reducing false stops. Welchman's diagonal board meant that the bomb would stop much less frequently on incorrect solutions, saving enormous amounts of verification time. The combination of Turing's core design and Welchman's enhancement created a truly effective tool. By the end of the war, over 200 bombs were in operation at Bletchley Park and its outstations, each named after places or people, running 24 hours a day. Breaking Enigma required more than just machines. It required cribs, and finding cribs required intimate knowledge of German military procedures and communication habits. Cryptanalysts at Bletchley Park studied German operational patterns obsessively. They learned that German weather stations sent reports at predictable times using predictable formats. They discovered that many situation reports contained a phrase, "nothing to report." They found that messages often began with formal address patterns or ended with Heil Hitler. German operators were human and made mistakes. They sometimes chose weak message keys, like AAA or their girlfriend's initials. Some operators developed recognizable habits that codebreakers could exploit. One particularly valuable source of cribs came from re-encodements. Sometimes the same information would be sent at different security levels using different Enigma keys or even different cipher systems. If Bletchley had already broken one version of a message, they could use it as a crib for the version encrypted with unknown settings. German forces in North Africa proved particularly prone to this, sometimes sending identical situation reports on both Wehrmacht and Luftwaffe networks. Another source was what cryptanalysts called gardening. This involved having RAF aircraft drop mines in specific locations, where German minesweepers would predictably report them using encrypted messages containing the known location coordinates. Naval Enigma proved far more difficult than Army or Air Force traffic. The German Navy used 8 rotors instead of 5. They maintained stricter communication discipline, and their operators made fewer mistakes. Additionally, naval messages were often shorter and contained more abbreviated technical terminology, making cribs harder to find. HUD-8, under Turing's leadership, struggled with naval Enigma throughout 1940 and early 1941. The breakthrough came not through cryptanalysis alone, but through capture operations that seized codebooks and cipher materials from German vessels before they could be destroyed. The capture of cipher materials from German weather ships and U-boats in May and June 1941 provided Bletchley Park with current naval Enigma codebooks. These captures were carefully orchestrated operations where the British would attack specific vessels, board them rapidly, and seize cryptographic materials before the crews could complete destruction procedures. The intelligence from these captures allowed HUD-8 to read naval Enigma traffic through much of 1941 and early 1942. This intelligence proved crucial for protecting Atlantic convoys and routing them away from U-boat wolf packs. Convoy losses dropped dramatically when Bletchley could read German naval communications. Then came the blackout. In February 1942, the German Navy introduced the 4-rotor Enigma M4 for U-boat communications. Overnight, Bletchley Park lost the ability to read U-boat traffic. The 4th rotor multiplied the problem's complexity by a factor of 26, and the existing bombs were not capable of handling it. Atlantic convoy losses soared during 1942 as U-boats operated with renewed effectiveness. Bletchley Park mounted a desperate effort to break back into U-boat Enigma. The breakthrough finally came in December 1942 when the U-boat U-559 was sunk in the Mediterranean, and British sailors boarded the sinking submarine to retrieve codebooks, though 2 of them drowned in the process. The recovered materials from U-559, combined with development of 4-rotor-capable bombs, allowed Bletchley to break back into U-boat Enigma by December 1942. The impact was immediate. In the first 5 months of 1943, the Allies sank over 100 U-boats, while convoy losses declined dramatically. May 1943 became known as Black May for the German submarine force, with 41 U-boats sunk. Admiral Donitz, commander of the U-boat fleet, temporarily withdrew his submarines from the North Atlantic, essentially conceding defeat in the Battle of the Atlantic. Bletchley Park's intelligence, code-named Ultra, had turned the tide of one of the war's most critical campaigns. Ultra intelligence had to be handled with extraordinary care to protect the source. If the Germans realized their codes were broken, they would change their procedures, and Bletchley would lose access. A complex system of security protocols governed how Ultra could be used. Military commanders who received Ultra intelligence were told it came from a highly placed spy or other fictional sources. Operations based on Ultra had to be disguised. If an Ultra decrypt revealed a convoy's location, aircraft would be sent on a visible reconnaissance mission first, so the subsequent attack could be attributed to aerial spotting rather than code breaking. Only a small number of people at the highest levels knew that Ultra came from reading Enigma. The process of transforming an intercepted radio transmission into actionable intelligence involved many stages. First, listening stations scattered across Britain and the Empire would intercept German radio transmissions and transcribe them. These intercepts would be sent to Bletchley Park by teleprinter. Cryptanalysts would identify cribs and set up bomb runs. When the daily keys were broken, a team of typists would decrypt the day's backlog of messages using Type-X cipher machines modified to simulate Enigma. The decrypted German text would then go to intelligence analysts who would translate, interpret, and assess the information. The most important intelligence would be sent immediately to military commanders via secure channels. The entire process, from interception to delivery, often took only a few hours. Different Enigma keys required different breaking techniques. The Germans used separate key systems for different military branches and theaters. Luftwaffe keys were generally easier to break due to more predictable message formats and more frequent cribs. Wehrmacht keys varied in difficulty. Some of the hardest keys were those used by the SS and German intelligence services, which maintained better communication security. The railway Enigma used by the Reichsbahn was actually one of the most consistently readable systems because railway personnel were less security conscious and their messages were highly formulaic. Intelligence from railway Enigma provided insights into German logistics and troop movements throughout the war. The human element at Bletchley Park was as important as the technology. The majority of staff were women, many recruited from universities or through personal connections to existing staff. These women worked as cryptanalysts, bomb operators, intercept operators, clerks, and intelligence analysts. The work was tedious and stressful, operating in shifts around the clock. The Official Secrets Act bound everyone to absolute silence about their work, not just during the war but for decades afterward. Many Bletchley veterans never told their own families what they had done during the war, taking the secret to their graves. The culture at Bletchley combined intense intellectual rigor with wartime urgency, creating an environment where academic brilliance could be applied directly to winning the war. Bletchley Park also pioneered the use of mechanical computation for code breaking. In 1943, a team led by mathematician Max Newman developed a machine called Heath Robinson, and then its successor Colossus, to break a different German cipher system called the Lorenz cipher. Colossus was arguably the world's first programmable electronic digital computer. While it wasn't used against Enigma directly, it represented the evolution of the mechanization principles that Turing and others had applied to Enigma. The combination of human analysis, mechanical testing, and emerging computer technology at Bletchley created a template for signals intelligence that continues to influence intelligence agencies today. The cooperation between different allied nations at Bletchley was essential to its success. The initial Polish contribution has already been discussed, but American cryptanalysts also made important contributions after the United States entered the war in December 1941. American codebreakers, particularly from the U.S. Navy's OP-20G unit, worked closely with Bletchley Park. They shared techniques, intelligence, and even manufactured bombs in the United States to supplement the British machines. This Anglo-American cryptanalytic cooperation laid the groundwork for the signals intelligence partnership that continues between the two countries to this day. The scale of the operation grew dramatically as the war progressed. By 1945, Bletchley Park employed over 10,000 people. The volume of intercepted traffic was enormous, with hundreds of thousands of messages processed annually. The bombs ran constantly, tested millions of possible settings, and consumed tremendous amounts of electrical power. Additional facilities were built around Britain to house bombs and other equipment. The operation required not just cryptanalysts and operators, but administrators, security personnel, maintenance engineers, catering staff, and transportation coordinators. Bletchley Park had become an industrial intelligence factory. The impact of ultra-intelligence on military operations was profound but difficult to quantify precisely. Historians generally agree that Ultra shortened the war, with estimates ranging from 6 months to 2 years. It certainly saved lives by helping protect convoys, anticipate German attacks, and target enemy forces more effectively. Ultra-intelligence played crucial roles in the North African campaign, where it revealed Rommel's supply problems and planned movements. It contributed to Allied success at the D-Day landings by helping to deceive Germans about the invasion location and confirming that the deception had worked. It enabled more effective targeting of German military production and transportation networks. However, Ultra was not omnipotent. The Germans changed keys daily, and sometimes Bletchley couldn't break particular keys quickly enough for the intelligence to be useful. Some keys were never broken at all. The Germans sometimes used other cipher systems or landline communications that Bletchley couldn't intercept, and even when messages were decrypted, they still required correct interpretation. There were failures and misunderstandings, but overall, the sustained ability to read a significant portion of German military communications provided the Allies with an enormous strategic advantage that the Germans never fully appreciated they had lost. The security of the ultra-secret was maintained throughout the war, which is itself remarkable. Despite tens of thousands of people knowing at least parts of the operation, and despite the extensive use of the intelligence in military operations, the Germans never definitively realized that Enigma had been broken. They investigated possible compromises several times, conducted inquiries into security breaches, and considered whether their codes might be vulnerable. But they consistently concluded that Enigma remained secure. Their faith in the mathematical strength of the system, combined with the Allies' careful deception about sources and methods, kept the secret safe until long after the war ended. The end of World War II did not end the story of the Enigma Machine. In many ways, the post-war chapter is just as fascinating as the wartime story. The secrets kept, the machines dispersed around the world, the influence on modern technology, and the eventual revelation of the truth created ripples that continue to this day. The Enigma's legacy extends far beyond its role in a single conflict, touching the very foundations of modern computing, cryptography, and intelligence work. When Germany surrendered in May 1945, the Allies faced a peculiar problem: what to do with thousands of captured Enigma machines. The British and Americans made a calculated decision that would have profound implications. They gathered up as many Enigma machines as possible and secretly distributed them to countries around the world, particularly to former colonies and developing nations. The recipients believed they were receiving secure encryption equipment. In reality, Britain and the United States could read all the traffic encrypted on these machines because they had retained all the technical knowledge from breaking Enigma during the war. This deception continued for decades, providing Western intelligence agencies with access to the diplomatic and military communications of dozens of countries. The extent of this post-war Enigma operation only became clear decades later. Countries in Africa, Asia, and South America used Enigma machines well into the 1970s, completely unaware that their communications were compromised. The British Government Communications Headquarters, or GCHQ, and the American National Security Agency, or NSA, could read their traffic effortlessly. This represented perhaps one of the most successful intelligence operations in history, turning the enemy's own captured equipment into a worldwide surveillance network. The countries using these machines trusted them because they came from sophisticated German engineering and seemed mathematically secure. They had no idea that the mathematical security had been defeated decades earlier. The full story of Bletchley Park and the breaking of Enigma remained classified for nearly 30 years after the war ended. The Official Secrets Act prevented any of the thousands of people who had worked there from discussing what they had done. Even as memoirs and histories of World War II proliferated in the 1950s and 60s, the Enigma story remained completely hidden. Military historians analyzed the war's campaigns without knowing about the intelligence advantage the Allies had possessed. German generals wrote their memoirs wondering how their plans had so often been anticipated, never learning that their communications had been compromised. The first public revelation came in 1974 with the publication of The Ultra-Secret by F.W. Winterbotham, a former RAF officer who had been involved in distributing ultra-intelligence during the war. The British government reluctantly allowed publication, finally acknowledging that Enigma had been broken. The book caused a sensation, forcing a complete reassessment of World War II history. Suddenly, battles and decisions that had seemed inexplicable made perfect sense when viewed through the lens of signals intelligence. The revelation vindicated some commanders whose decisions had been criticized and complicated the reputations of others. Even after Winterbotham's book, much remained classified. The full extent of the Polish contribution wasn't widely known until the late 1970s. The specific technical details of how Enigma was broken remained secret into the 1980s. Information about the bombs and other equipment was gradually declassified throughout the 1980s and 90s. The last major secrets, including details about some specific operations and the post-war distribution of Enigma machines to unsuspecting countries, only emerged in the 21st century. The slow pace of declassification reflected the ongoing sensitivity of signals intelligence methods and the desire to protect current operations. Alan Turing's role in breaking Enigma was particularly obscured for decades. Turing had died in 1954 under tragic circumstances, convicted of homosexuality, which was then a crime in Britain, and subjected to chemical castration. He died from cyanide poisoning, officially ruled a suicide, though some have questioned this verdict. Because his work at Bletchley Park was classified, he received no public recognition during his lifetime for his contributions to winning the war. When the Enigma story finally emerged, Turing was recognized posthumously as a hero. In 2013, he received a royal pardon, and in 2019, his image was selected to appear on the Bank of England's £50 note, cementing his status as one of Britain's most important historical figures. The influence of Enigma and Bletchley Park on the development of modern computing cannot be overstated. Turing's theoretical work on computation, which he had developed before the war, was directly applied to the practical problem of breaking Enigma. The Bombe machines were early examples of automated logical processing. Colossus, developed at Bletchley for breaking the Lorenz cipher, was a genuine electronic programmable computer. Many of the mathematicians and engineers who worked at Bletchley Park went on to pioneer the computer industry after the war. They brought with them concepts of automated data processing, logical circuits, and machine computation that they had developed for code breaking. The computer revolution of the late 20th century has direct roots in the cryptanalytic work done against Enigma. Modern cryptography also owes a debt to the Enigma experience. The realization that even mathematically strong systems could be vulnerable to determined cryptanalysis influenced the development of new encryption methods. Claude Shannon, the founder of information theory, worked on cryptography during World War II and later published fundamental papers on cryptographic security that drew on wartime lessons. The concept of computational security, where a cipher is considered secure if breaking it requires an infeasible amount of computation, emerged partly from analyzing what went wrong with Enigma. Modern cipher design explicitly considers resistance to the kinds of attacks that defeated Enigma: pattern analysis, known plaintext attacks, and related key attacks. The institutional legacy of Bletchley Park also shaped the modern intelligence world. The cooperation between British and American codebreakers during the war evolved into the UCUSA Agreement of 1946, which formalized signals intelligence sharing between the two countries. This agreement later expanded to include Canada, Australia, and New Zealand, creating what became known as the Five Eyes Alliance. This partnership, born from the Enigma experience, remains one of the most significant intelligence sharing arrangements in the world. The organizational structures, methodologies, and even some of the facilities established during the Enigma era continued to evolve into the modern signals intelligence apparatus that monitors global communications today. Bletchley Park itself faced an uncertain future after the war. The site was returned to civilian use, and many of the wartime huts were demolished or fell into disrepair. For decades, it seemed destined for redevelopment. In the 1991, a trust was formed to preserve the site as a museum. Today, Bletchley Park is a major heritage attraction, receiving hundreds of thousands of visitors annually. The mansion has been restored. Several of the huts have been preserved and furnished as they were during the war, and working replicas of the bomb machines are on display. The site serves as both a memorial to those who worked there and an educational resource for understanding this crucial period in history. Original Enigma machines have become highly sought-after collector's items. Since the declassification of the Enigma story, these machines have commanded increasingly high prices at auction. In 2015, an Enigma machine sold at Christie's auction house for over $260,000. Another sold in 2017 for nearly $320,000. A rare four-rotor naval Enigma M4 could command even higher prices. The machines are prized not just for their historical significance, but as beautiful examples of mechanical engineering and as tangible connections to one of history's most important technological stories. Museums around the world now have Enigma machines in their collections. The Imperial War Museum in London has several examples. The National Cryptologic Museum near Fort Meade, Maryland, home of the NSA, has an extensive collection. The Deutsches Museum in Munich displays German examples with historical context. The museum at Bletchley Park naturally has the most comprehensive collection, including machines, rotors, plug boards, and associated equipment. These displays educate new generations about cryptography, the importance of signals intelligence, and the human stories behind the technology. Several working Enigma machines and bombs have been reconstructed by enthusiasts and educational institutions. These reconstruction projects require extensive research, mechanical engineering skill, and electrical expertise. Building a working bomb is particularly challenging because detailed construction plans were destroyed after the war. Engineers have had to work from photographs, surviving fragments, and the memories of veterans to recreate these machines. These reconstructions serve as teaching tools, allowing people to see and sometimes operate the actual mechanisms that made history. There's something profoundly educational about watching rotors spin and lamps illuminate as you type a message into a working Enigma. The Enigma story has captured popular imagination, inspiring numerous books, documentaries, films, and television programs. The 2014 film The Imitation Game, starring Benedict Cumberbatch as Alan Turing, brought the story to mainstream audiences worldwide, though it took dramatic liberties with historical facts. Numerous documentaries have explored different aspects of the Enigma story, from technical explanations to personal memoirs of Bletchley Park veterans. Academic conferences regularly examine new research and newly declassified documents. The story continues to fascinate because it combines technology, mathematics, espionage, war, and human drama in a uniquely compelling package. The ethical questions raised by the Enigma story remain relevant today. The decision to keep the breaking of Enigma secret and to distribute captured machines to unsuspecting countries raises questions about the morality of signals intelligence. The treatment of Alan Turing, convicted and punished for homosexuality despite his contributions to winning the war, highlights the injustices of the era. The fact that thousands of people at Bletchley Park kept silent for decades about their work demonstrates both admirable discipline and the personal cost of secrecy. These issues resonate in contemporary debates about surveillance, privacy, government secrecy, and the rights of individuals versus national security. The technical lessons from Enigma remain vital for understanding cryptographic security. Enigma failed not because the basic mathematical principle was flawed, but because of implementation details, operational procedures, and human factors. The machine's inability to encrypt a letter as itself gave codebreakers a crucial clue. The German message procedures, particularly the early double encryption of message keys, created exploitable patterns. Operator errors, message repetitions, and predictable content provided the cribs that made breaking possible. Modern cryptographers study these failures to avoid repeating them. The principle that security depends not just on mathematical strength, but on proper implementation and operational discipline is an Enigma lesson that remains critical. Education about cryptography and cybersecurity often begins with the Enigma story because it makes abstract mathematical concepts tangible and historically relevant. Students can understand substitution ciphers, permutations, and computational complexity through examining how Enigma worked and how it was broken. The human element, the race against time, and the high stakes make the story engaging while teaching serious concepts. Many university cryptography courses include sections on Enigma, and it features prominently in computer science history curricula. The machine serves as a perfect case study for understanding both historical cryptography and the principles that underlie modern encryption. The preservation of institutional memory about Enigma has been challenging. Many Bletchley Park veterans died before the story was declassified, taking their detailed memories with them. Others who lived to see the revelations were elderly when they could finally speak, and their recollections were sometimes imperfect after decades of silence. The destruction of equipment and documents after the war eliminated much physical evidence. Historians have had to piece together the story from fragmentary records, personal diaries kept in violation of security rules, photographs, and the testimony of survivors. This process continues as researchers discover new documents in archives or as additional materials are declassified. The Enigma cipher has inspired modern cryptographic challenges and educational exercises. Numerous websites and software programs allow people to experiment with simulated Enigma encryption. Cryptography courses often assign projects involving implementing Enigma algorithms or trying to break sample messages. These exercises help students understand both historical cryptanalysis and gain intuition about modern cryptographic concepts. Some organizations have created Enigma-themed puzzles and competitions, challenging participants to decrypt messages using limited information, recreating in miniature the challenges faced by Bletchley Park cryptanalysts. Recognition for the Bletchley Park veterans gradually improved after declassification. Many received honors and awards decades after their service. The British government created commemorative medals for those who served in signals intelligence during the war. Universities awarded honorary degrees to surviving cryptanalysts. Public ceremonies celebrated their contributions. However, many veterans expressed mixed feelings about finally being recognized. Some were proud to have their work acknowledged, while others felt the recognition came too late for colleagues who had died in obscurity. Some maintained that they had simply done their duty and needed no special recognition. The delayed gratitude highlighted the personal sacrifices required by decades of enforced secrecy. The Enigma story has become a symbol for the broader importance of mathematics and science in modern life. The fact that mathematicians and scientists made decisive contributions to winning World War II challenged traditional hierarchies that privileged military or political leadership. The recognition of Bletchley Park's importance validated the investment in education, research, and intellectual pursuits. Many science and technology advocates point to Enigma when arguing for government funding of research or STEM education. The story demonstrates that abstract mathematical knowledge can have urgent practical applications, even if those applications aren't immediately obvious. Finally, the Enigma machine stands as a reminder of human ingenuity applied to both creation and destruction. German engineers created a remarkable device that represented the cutting edge of cryptographic technology. Polish, British, and American mathematicians rose to the challenge of defeating it through equally impressive intellectual achievement. The machine enabled Germany to coordinate massive military operations across a continent. Breaking the machine helped the Allies counter those operations and ultimately win the war. The Enigma embodies both the potential and the danger of technology, the importance of innovation, and the eternal competition between those who make codes and those who break them. Its story, from invention to breaking to legacy, remains one of the most fascinating chapters in the history of technology, warfare, and human achievement.